Mars is not just difficult to live on. It may be impossible to survive there long term. That idea sounds wrong at first. You hear constant talk about colonies, cities, and a second home for humanity. Rockets are getting stronger. Technology is advancing fast. The dream feels close, but beneath that excitement, there is a deeper truth that most people never hear. The problem is not just engineering. The problem is physics. There are scientists who argue that no matter how advanced technology becomes, Mars may never support stable human life over long periods of time. Not because we are not smart enough, not because we lack resources, but because the planet itself works against us in ways that are almost impossible to overcome. This video breaks that down. You will learn why landing on Mars is only the beginning of the problem. You will learn why staying alive there for years or decades is a completely different challenge. You will see how radiation, gravity, atmosphere, and isolation combine into one system that pushes human survival to its limits. And most importantly, you will understand why some physicists believe that Mars is not a backup plan at all. There is a powerful illusion surrounding Mars. It looks familiar. It has days similar to Earth. It has seasons. It even has polar ice. From a distance, it feels like a colder, emptier version of home. That illusion makes people believe that with enough effort, Mars can be turned into a second Earth. But that similarity is only surface level. Mars is missing critical features that make life on Earth possible, and those missing pieces are not easy to replace. In fact, some of them may be impossible to recreate on a planetary scale. Here is something that most people do not realize. Every environment on Earth, no matter how extreme, still exists under the protection of Earth systems. Even the harshest deserts, the coldest polar regions, and the deepest oceans still benefit from Earth's magnetic field, atmosphere, and stable gravity. Mars has none of that protection. So the question is not whether humans can reach Mars. That part is already proven. Machines have landed there. Rovers have explored its surface. The real question is much more serious. Can humans actually live there for generations? Can a child be born, grow, and grow old on Mars without constant risk? Can a society exist there without depending on Earth for survival? These are the questions that change everything. Now, most discussions focus on the first step, getting humans to Mars, building the first base, planting a flag. But those are short-term goals. They last months or a few years at most. Long-term survival is a different game entirely. It requires stable food production, reliable protection from radiation, a safe atmosphere, healthy gravity conditions, mental stability over isolation, and systems that can run without failure for decades. Mars challenges every one of these. And here is where the tension begins to rise. Each problem on its own looks solvable. Engineers can design better habitats. Scientists can create new materials. Advanced systems can recycle air and water. These solutions sound promising when viewed individually, but when all of these problems combine, they create a chain of dependencies. One failure leads to another. One weakness exposes everything else. This is where the argument shifts from difficult to potentially impossible. Some physicists, including voices like Greene, point toward a deeper issue. Nature is not neutral. It sets limits. And sometimes those limits are not meant to be crossed no matter how advanced the civilization becomes. Mars may be one of those limits. This is not about fear. This is about understanding reality at its most fundamental level. Space exploration is one of humanity's greatest achievements. It pushes boundaries. It expands knowledge. But not every destination is equal. Some places can support life with effort. Others resist it completely. Mars sits in a strange middle ground. It is close enough to reach, familiar enough to attract us, but hostile enough to challenge every system we depend on. That combination makes it dangerous in a unique way. because it gives hope while hiding the true scale of the problem. Another lesser-known fact is how fragile human life really is outside Earth. The human body evolved under very specific conditions. Gravity, pressure, radiation levels, and atmospheric composition all shaped how the body functions. Even small changes can cause serious damage over time.
Mars does not offer small changes.
It offers extreme differences, and those differences act constantly, every second, every day, without pause. There is no natural protection layer, no easy adaptation, no quick fix. This means survival on Mars is not just about building machines. It is about fighting an entire planetary environment that was never meant for human life. So as the dream of colonizing Mars grows, stronger, a critical question becomes impossible to ignore. Are we trying to adapt Mars to humans, or will we be forced to adapt humans to Mars? Because those are two very different paths. One involves engineering solutions. The other may require changing what it means to be human. That idea sounds extreme. But when you look at the challenges closely, it starts to feel less like science fiction and more like a real possibility. And that is exactly what this video will explore. Not the surface level excitement, not the headlines, but the deeper reality that sits underneath all of it. By the end, you will see Mars in a completely different way. Not just as a destination, but as a test of the limits of human survival. Welcome to the channel. If you are curious about the real science behind space and the truths that most people overlook, subscribe now and stay with us until the end. Getting to Mars is not the hardest part. Getting down safely is where the real danger begins. Mars looks calm from orbit, a silent red surface, no oceans, no storms that look violent from space. But the moment a spacecraft starts its descent, the planet turns into a trap. The atmosphere of Mars creates a strange problem. It is too thin to help you, but it is also too thick to ignore. On Earth, the atmosphere is dense. Spacecraft use it to slow down. Heat shields burn, parachutes deploy, the air does most of the work. On the Moon, there is no atmosphere at all. Landing is controlled with rockets only, clean and predictable. Mars sits in between, and that is where everything goes wrong. The air on Mars is about 1% as dense as Earth's. That means it cannot slow a spacecraft enough during entry. A vehicle enters at extreme speed, around 20,000 kilometers per hour. It hits the atmosphere. Heat builds up fast. The heat shield glows. The surface burns. But the air is not thick enough to reduce speed to safe levels. Then comes the next problem: parachutes. On Earth, parachutes are reliable. On Mars, they barely work. The thin air does not create enough drag. Even the largest supersonic parachutes ever built struggle to slow down small robotic probes. They shake violently. They push materials to their limits. Now think about scaling this up. A human mission is not a small rover. It is a massive system. Crew habitat, life support, supplies for months or years. All of that adds weight, a lot of weight, and heavier objects fall faster. This creates a deadly chain reaction. The spacecraft is too heavy for the thin atmosphere to slow. Parachutes are not strong enough to handle the load, and rockets must do the final braking. But rockets need fuel. Fuel adds more weight. More weight makes the landing even harder. This is not a simple engineering issue. It is a loop with no easy exit. There is something else that most people do not know. The timing of every step during Mars landing must be perfect. There is almost no room for correction. The delay in communication between Earth and Mars means there is no real-time control. The spacecraft must land itself. Autonomous systems handle everything: entry angle, speed control, parachute deployment, heat shield separation, rocket ignition. If any one of these steps is even slightly off, the mission fails. Past missions show how close this margin is. Several spacecraft sent to Mars have crashed. Some burned up. Some hit the surface at high speed. Even with decades of experience, success is never guaranteed. And those were small robotic missions. Now consider humans inside. The system must be far more reliable, far more precise, far more powerful. One more hidden danger is the surface itself. Mars is not flat. There are rocks, slopes, dust, and uneven terrain. Landing zones must be carefully selected. Even then, hazards remain. Dust adds another layer of risk. It can interfere with sensors during descent. It can reduce visibility. It can affect engine performance during the final landing phase, so the spacecraft is falling fast. The atmosphere is not helping enough. The parachute is struggling. Rockets are firing to slow it down. The system is making split-second decisions on its own, and the ground is coming closer. All of this must work perfectly, every single time, and this is just the landing. The danger on Mars does not always come with noise or impact. It comes silently every second, passing straight through the human body. Mars has no global magnetic field. That single fact changes everything. On Earth, the magnetic field acts like a shield. It deflects charged particles coming from the sun and from deep space. Without it, life on Earth would look very different if it existed at all. Mars lost this protection billions of years ago. Scientists believe its core cooled and the magnetic field collapsed. Since then, the planet has been exposed, fully exposed. Space is not empty. It is filled with high energy particles. Cosmic rays travel at near light speed. Solar radiation bursts out during solar flares. These particles carry enormous energy, and on Mars there is nothing strong enough to stop them. The atmosphere is too thin to block them. The surface offers no natural shield, so the radiation reaches the ground, and it reaches anything living on it. This is where the real danger begins. Radiation does not kill instantly. That is what makes it more dangerous. It builds up over time. It damages DNA. It breaks molecular bonds inside cells. It creates mutations. These mutations can lead to cancer, but that is only one part of the problem. Recent studies suggest that long-term exposure to cosmic radiation can also affect the brain. It may damage neurons. It may reduce cognitive function. It may even change behavior over time. That means a person living on Mars is not only at risk physically, but also mentally. And the exposure is constant, day and night, every hour, every minute. Even during sleep, there are no safe periods. Astronauts in low Earth orbit are still protected by Earth's magnetic field. Even then, they face higher radiation levels than people on the ground. Missions are limited in duration because of this. Mars is far worse. The radiation dose on the Martian surface is significantly higher. Over a long mission, it can exceed safe limits by a wide margin. Now think about long-term settlement. Years, decades, generations. The human body is not designed for that. Shielding becomes the only option, but shielding is not simple. To block radiation effectively, you need thick layers of material, not just thin walls, dense mass. Materials like water, concrete, or specially designed composites. This adds enormous weight. Transporting that weight from Earth is extremely difficult and expensive. Building it on Mars requires infrastructure that does not yet exist. Some scientists suggest using the planet itself, living underground, using Martian soil as a barrier. This idea is not optional. It may be necessary for survival, but that creates another problem. Living below the surface means isolation, no natural light, no open sky, no direct connection to the outside world. It turns a colony into a buried system, cut off from its environment. There is also a lesser-known threat, solar flares. When the sun releases a powerful burst of radiation, levels can spike suddenly. On Earth, the magnetic field absorbs most of it. On Mars, that burst can hit the surface directly. Without warning, without protection A. Strong solar event during surface activity could be deadly in a short time. So every mission must monitor the sun constantly. Every shelter must be ready to handle sudden radiation spikes. This is not a one-time challenge. It is a permanent condition. Radiation does not weaken. It does not stop. It does not give second chances. And even if a solution is built, it must work perfectly all the time for years without failure. Because outside that protection, the environment is always waiting. Breathing on Mars is not difficult. It is impossible. The air looks real. It moves. It forms clouds. It even creates weather. But it cannot support human life for even a few seconds. Mars has an atmosphere made of about 95% carbon dioxide. Oxygen is almost absent. On Earth, oxygen makes up about 21% of the air. That difference is not small. It is the difference between life and death. But the composition is only part of the problem. The pressure is far worse. The atmospheric pressure on Mars is less than 1% of Earth's at sea level. That means the air is not just unbreathable. It is too thin to keep the human body stable. At that pressure, liquid water cannot exist on the surface for long. It either freezes or turns into vapor almost instantly. And the human body depends on liquid water in every cell. Exposure to such low pressure causes a dangerous effect. Bodily fluids can begin to boil at normal body temperature. Not like boiling water on a stove, but a slow formation of vapor inside tissues. This is called ebulism. It is not survivable without immediate protection. So any human presence on Mars must be inside a fully pressurized system, a suit or a habitat. Every second, there is no safe exposure. Not even briefly, and this creates a fragile situation. Because pressure systems must be perfect. Even a small leak can become deadly. A tiny crack, a weak seal, a damaged valve. Any failure allows air to escape. Pressure drops. Oxygen levels fall. The body begins to shut down within minutes. There is no backup from the environment, no air to breathe, no pressure to stabilize the body. Only vacuum-like conditions waiting outside. This makes every structure on Mars a life support system. Walls are not just walls. They are barriers between survival and instant danger. Now consider long-term settlement. Habitats must hold pressure for years, without failure, under constant stress from temperature changes and dust exposure. Materials expand and contract, seals wear out, systems degrade, maintenance becomes a constant battle. And there is another layer that is often overlooked, producing oxygen. Mars has carbon dioxide. That can be used to create oxygen through chemical processes. Some experiments have already shown this is possible on a small scale. But scaling this to support a colony is a massive challenge. It requires energy, reliable systems, continuous operation. Any interruption in oxygen production becomes critical very quickly. Then comes the idea many people talk about, terraforming, turning Mars into a planet with a thick, breathable atmosphere. It sounds like a solution, but the reality is far more complex. To thicken the atmosphere, massive amounts of gas must be released or generated. This would require heating the planet, releasing carbon dioxide trapped in ice and soil, or importing gases from elsewhere. Even if this process started, it would take centuries, possibly thousands of years. And there is a deeper problem. Mars does not have a strong magnetic field. Without it, any atmosphere that builds up can slowly escape into space. Solar wind strips it away over time. This is one reason Mars lost its thicker atmosphere in the past. So even if humans create a new atmosphere, the planet may not be able to hold it. That turns terraforming into a temporary fix at best. There is no realistic short-term solution that creates open-air survival. So every human on Mars remains inside a controlled bubble, dependent on systems that must never fail. Because outside that thin barrier, the air is not just unbreathable. It is almost not there at all. Cold on Mars is not just uncomfortable. It is constant, deep, and unforgiving. The average temperature sits around minus 60 degrees Celsius. That is colder than most places on Earth ever reach. And that is only the average. Nights can drop far lower. In some regions, temperatures can fall below minus 100 degrees Celsius. At those levels, exposed equipment becomes brittle. Materials contract, metals can weaken over time, seals can crack, systems that work perfectly on Earth begin to fail under stress. And the cold is not stable. Mars experiences sharp temperature swings. Day and night cycles create rapid changes. A surface that warms slightly under sunlight can freeze again within hours. This repeated expansion and contraction puts constant pressure on structures. Over time, even strong materials begin to degrade. There is another factor that makes this worse: the thin atmosphere. On Earth, the atmosphere helps distribute heat. It softens temperature changes. On Mars, that effect is weak. Heat escapes quickly. Cold returns fast. There is little buffer, so every habitat must fight to maintain a stable internal temperature. Heating systems must run continuously. Energy demand rises. Any failure in heating becomes dangerous very quickly. But temperature is only part of the threat. Mars has weather, and that weather can take over the entire planet. Dust storms on Mars are not like storms on Earth. They can grow to cover vast regions. Sometimes they expand until they wrap around the entire planet. These global dust storms can last for weeks, even months. During that time, sunlight is blocked. The sky turns dark. The surface becomes covered in fine dust that moves with the wind. This creates a serious problem for power. Many Mars mission designs depend on solar energy. Panels collect sunlight and convert it into electricity. But during a dust storm, sunlight drops sharply. Power generation falls. At the same time, dust settles on the panels. It forms a layer that blocks even more light. Over time, energy output can drop to critical levels. This is not just a temporary inconvenience. It can threaten survival. Past robotic missions have already faced this problem. Some lost power completely and never recovered. Now consider a human colony. Life support systems need constant energy, oxygen, production, heating, communication, water recycling, all depend on power. A long dust storm can push these systems to their limits. There is also the issue of the dust itself. Martian dust is extremely fine, much finer than typical sand on Earth. It can stick to surfaces. It can enter small openings. It can interfere with mechanical parts. Over time, it wears down equipment. It can damage seals. It can reduce efficiency in moving systems. It can even affect electronics. And once it gets inside, it is difficult to remove. For humans, the dust presents another risk. If it enters living spaces, it can affect air quality. Some studies suggest that Martian dust may contain toxic compounds, including perchlorates, which can be harmful to the human body. So every system must be sealed, filtered, protected all the time. This creates a constant state of pressure. Every component must perform under extreme cold, shifting temperatures, and a dusty environment that never truly settles. There is no season where conditions become easy. The planet does not calm down. It continues to test every structure, every machine, and every human system without pause. And over time, even small weaknesses begin to show. Gravity on Mars feels gentle at first. Lighter steps, easier movement, less effort to lift heavy objects. It sounds like an advantage, but the human body is not designed for that environment. Mars has only about 38% of Earth's gravity. That difference changes how every system in the body behaves. Bones, muscles, blood flow, even internal organs all depend on gravity to function normally. On Earth, gravity constantly pulls down. The body adapts to that force from birth. Bones grow strong under pressure. Muscles stay active just to maintain posture. The heart works against gravity to move blood upward. Remove most of that force, and the system begins to drift. Evidence from space already shows this. Astronauts in orbit experience microgravity. Even with daily exercise, they lose bone density. Muscles shrink. Strength decreases. The longer they stay, the greater the loss. On Mars, gravity is not zero, but it may not be enough. That is the unknown. There is no long-term data on how humans respond to partial gravity over years or decades. No one has lived in that environment long enough to understand the full effects. But scientists have strong concerns. Bone density loss is one of the most serious. Bones require constant stress to stay strong. Without it, they weaken, calcium is lost, fracture risk increases. Over time, this can become severe. Muscle loss follows a similar pattern. The body reduces muscle mass when it is not needed. Movement becomes easier, but strength fades. Even basic tasks may become harder over time as the body adapts to lower demand. The cardiovascular system also changes. In low gravity, blood does not pool in the lower body as it does on Earth. Fluid shifts upward. This can affect heart function. It can alter blood. Pressure regulation. Some astronauts report vision problems linked to these fluid changes. Now extend this over years or generations. The effects could become permanent. Children born in lower gravity might develop differently. Bones may form with less density. Muscles may not reach Earth-level strength. The entire body structure could change. Returning to Earth after long exposure could be extremely difficult. The body may not tolerate full gravity anymore. There is also concern about internal organs. Their position and function depend partly on gravity. Changes in pressure and orientation could affect digestion, lung function, and other systems in ways that are not fully understood. This creates a long-term risk that is not easy to measure. Now consider solutions. Artificial gravity is often suggested. Rotating habitats could create a force similar to gravity through centrifugal motion. In theory, this could protect the human body, but in practice, it is extremely complex. Large, rotating structures must be built. They must be stable. They must run continuously without failure. Any malfunction could be dangerous. On the surface of Mars, creating such systems becomes even more difficult. There is no simple way to increase gravity across an entire settlement. So humans would need to live in an environment that slowly changes their bodies over time. And there is no guarantee that the changes are reversible. This is not just a health issue. It is a question of long-term survival as a species in that environment, because if the human body cannot maintain its structure and function under Martian gravity, then permanent settlement faces a problem that technology alone may not solve. And while the surface challenges are visible, this one works quietly from within. On Mars, survival depends on a simple rule. Everything you need must either come with you or be built from what is already there. There are no supply chains, no nearby cities, no quick deliveries. Every kilogram sent from Earth costs enormous energy and money. That limits how much can be transported. So most systems must rely on local production: air, water, food, fuel. Each one requires its own process. Each process requires energy, machinery, and maintenance.
And each one must work without failure.
This creates a tightly connected system. Oxygen production depends on power. Power depends on equipment that must stay clean and functional. Water recycling depends on filters that must be replaced or repaired. Food production depends on controlled environments, stable temperatures, and constant monitoring. If one system fails, others begin to struggle. This is not like life on Earth where backup options exist. On Mars, there is no backup outside the system. There is also a lesser-known detail about life support systems. They do not just need to work. They need to work continuously without interruption for long periods of time. Even small fluctuations can become dangerous. A slight drop in oxygen levels, A small contamination in water, a short power loss, these are not minor issues. They can escalate quickly. And repairs are not always simple.
Spare parts are limited.
Tools must be carefully managed. Complex systems may require expertise that is not available on site. Every repair becomes a critical operation. Now add distance into the equation. Mars is far from Earth. At its closest, it is tens of millions of kilometers away. At its farthest, much more. Communication is not instant. Signals take time to travel. Depending on the position of the planets, the delay can reach up to 20 minutes one way. That means a message sent from Mars can take 20 minutes to reach Earth. A reply takes another 20 minutes. In an emergency, there is no immediate help, no real-time guidance, no quick instructions, no direct control from Earth. Every decision must be made locally. This changes how missions operate. Astronauts must be highly trained. Systems must be autonomous. Artificial intelligence may play a role in managing operations, but even with advanced systems, uncertainty remains. Unexpected problems can arise. Conditions can change. And without instant support, the margin for error becomes smaller. Then there is the human factor. Isolation on Mars is not just physical, it is psychological. A small group of people living in a confined space, surrounded by a hostile environment, cut off from Earth by distance and delay. The sky looks different. The landscape is empty. There is no natural life, no trees, no oceans, no familiar sounds. Over time, this can affect the mind. Studies from isolated environments on Earth, such as polar stations and underwater habitats, show increased stress, mood changes, and tension between crew members. Mars amplifies these conditions. The confinement is longer, the distance is greater, the sense of separation is deeper. Even communication with family feels distant. Conversations are delayed. Emotional connection becomes harder to maintain. There is also the pressure of constant awareness. Every person knows that survival depends on systems working perfectly. Every sound, every alert, every small issue carries weight. This creates a background level of stress that never fully disappears. And unlike short missions, long-term settlement means there is no clear end point, no quick return, no simple exit. Life becomes a continuous effort to maintain stability in a place that offers none naturally. And in that environment, both machines and minds are pushed to their limits. Mars is not just a difficult place. It is a place that works against life at every level. The surface looks quiet, but beneath that silence is a system filled with constant pressure, thin air that cannot support breathing, radiation that never stops, cold that weakens materials, dust that covers everything, gravity that slowly changes the human body, distance that cuts off help when it is needed most. Each of these problems has a
Possible solution on its own. Better shielding,
stronger habitats, advanced life support, smarter machines.
these ideas sound powerful when viewed one by one.
But Mars does not present these challenges one at a time.
It delivers all of them together.
At the same time, every day, without pause. And that is where the real problem begins. Because solving one issue often makes another harder. Adding protection increases weight. More weight makes landing more dangerous. More systems require more power. More power systems create more points of failure. It becomes a chain where every link depends on another. This is why some scientists argue that Mars is not just hard. It may be beyond the limit of sustainable human life as we know it. Not because of a single barrier, but because of the combined force of all of them. This raises a deeper question. Are humans meant to live everywhere they can reach? Or are there boundaries that even advanced technology cannot fully overcome?
Mars may be
one of those boundaries, and if humans do choose to stay there long-term, survival may require more than machines and engineering. It may require changing the human body itself, adapting to lower gravity, living underground, depending entirely on artificial systems, at that point, the line between human and something new begins to blur. That is the real cost of living on Mars. If you found this breakdown useful, support the channel with a like and subscribe for more deep explorations into space and science.